In the world of technology, there are big leaps, and then there are reality-bending revolutions. Quantum computing belongs to the second category. These machines, built on the mind-bending rules of quantum mechanics, promise to solve problems so complex they would take today's best supercomputers billions of years. But this incredible power is built on a foundation of almost unimaginable fragility. The heart of a quantum computer, the qubit, is a delicate wisp of information, constantly at risk of being wiped out by the noisy world around it. And one of its greatest enemies is completely invisible: magnetism. Today, we're exploring the incredible story of the invisible armor that protects the quantum realm, the science of magnetic shielding. To understand why scientists are building what are essentially magnetic black holes in their labs, we first need to understand the qubit. A regular computer bit is simple. It's a switch, either on or off, a 0 or a 1. A qubit, however, is a different beast entirely. Thanks to a quantum property called superposition, a qubit can be a 0, a 1, or a combination of both at the same exact time. This ability to exist in multiple states at once gives quantum computers their power. With just 300 qubits in superposition, a computer could hold more possible values than there are atoms in the known universe. But it gets weirder. Qubits can also be linked by a spooky phenomenon called entanglement. When two qubits are entangled, they are connected in a profound way. Measuring one instantly affects the other, no matter how far apart they are. Albert Einstein famously called this spooky action at a distance. By harnessing superposition and entanglement, quantum computers can explore a vast number of solutions simultaneously, finding the right answer in a way that is fundamentally different and potentially exponentially faster than any classical computer. Scientists are building these qubits from all sorts of things. Some use tiny circuits of metal cooled to temperatures colder than deep space, becoming superconductors with zero electrical resistance. Others trap individual atoms in electromagnetic fields. Some even encode information in the spin of a single electron. But no matter what they're made of, all qubits share a fatal weakness. They are hypersensitive to their environment. The quantum state is a fleeting thing. The superposition and entanglement that make qubits so powerful are incredibly fragile. The slightest vibration, a change in temperature, or a stray bit of energy from the outside world can cause the whole system to collapse. This loss of quantumness is called decoherence. It's when the qubit unwillingly interacts with its environment and its complex quantum state. That mix of 0 and 1 snaps into a simple classical 0 or 1, erasing the calculation in progress. Decoherence is the single biggest obstacle to building a large, useful quantum computer. The length of time a qubit can hold its state is called its coherence time. And right now, we're often talking about millionths or thousandths of a second. It's a frantic race to complete a calculation before the quantum state simply evaporates. While many things can cause decoherence, one of the most persistent and damaging culprits is magnetic noise. Stray magnetic fields are everywhere. The Earth itself has a magnetic field. The power lines in the walls, the motors and lab equipment, even the very electronics used to control the qubits, all generate magnetic fields. For the most promising types of qubits, like superconducting circuits and spin qubits, this magnetic noise is devastating. Superconducting qubits are based on precise electrical currents, and a stray magnetic field can induce unwanted currents, messing up their energy levels and destroying the superposition. In fact, the technology that led to these qubits was first invented as an ultra-sensitive magnetic field detector. Spin qubits, which use the magnetic orientation of a particle, are even more directly vulnerable. An external magnetic field can literally knock the spin off course, erasing the information it holds. As you pack more and more qubits together, the problem gets worse. The magnetic pulse used to control one qubit can spill over and disturb its neighbors, an issue called crosstalk. To give these delicate qubits a chance to do their work, they need to be isolated in a sanctuary of profound magnetic silence. This is where the amazing science of magnetic shielding comes in. The most direct way to block a magnetic field is to wrap your sensitive device in a special material. This is called passive shielding. The goal isn't to stop the magnetic field, but to give it a much easier path to travel. The shield acts like a magnetic superhighway, guiding the field lines around the protected area, leaving the inside quiet. Think of it like a lightning rod, which doesn't stop the lightning, but provides a safe path for the electricity to go around a building and into the ground. For this job, the material of choice is a special nickel-iron alloy called mu metal. The mu in its name comes from the Greek letter used to represent magnetic permeability, a measure of how easily a material can support a magnetic field. Mu metal has an incredibly high permeability, meaning it effectively sucks in magnetic field lines from the surrounding space, concentrating them inside the shield material and far away from the fragile qubits. But building an effective shield is a serious engineering challenge. You can't just make a simple box. If the outside magnetic field is too strong, it can overwhelm a single layer of mu metal, causing it to become saturated and useless. So engineers use a clever design, multiple, nested shields, like a set of Russian Matryoshka dolls. The outermost layer takes the biggest hit from the external field, and each layer inside it reduces the field even more, creating a progressively quieter magnetic zone. Often, they combine materials, using an outer layer of plain soft iron to handle the strong fields, and inner layers of high permeability mu metal to mop up the tiny residual fields. The challenge gets even harder because many quantum computers operate at cryogenic temperatures, just fractions of a degree above absolute zero. At these temperatures, the properties of materials can change dramatically. Standard mu metal becomes less effective when it gets that cold. This has led to the development of specialized cryogenic alloys, with names like cryophy, designed specifically to maintain their high permeability even when cooled to near -270 degrees Celsius. In these deep freeze environments, engineers have another trick up their sleeve: superconductors. When a material becomes superconducting, it exhibits a bizarre property called the Meissner effect. It actively expels all magnetic fields from its interior. This makes a superconductor a perfect magnetic shield. Often, the very innermost layer of shielding, the one closest to the quantum chip, is made of a superconducting material, like aluminum or niobium, providing the final, ultimate layer of protection. Fabricating these shields is a delicate art. The amazing properties of mu metal come from its crystal structure, which is extremely sensitive. If you bend, cut, or weld the material, you ruin its permeability. After any machining, every component has to go through a special heat treatment called annealing. It's heated to a high temperature in a hydrogen atmosphere and then cooled down very slowly. This process restores the crystal structure and makes the material magnetically soft again. Finally, a quantum computer isn't a sealed box. It needs dozens, even hundreds of wires and cables running inside to control and read out the qubits. Every hole or seam in the shield is a potential leak where magnetic fields can sneak in. Engineers have to design clever overlapping seams and labyrinthine seals to block these leaks and maintain the magnetic silence inside. Passive shielding is the powerful first line of defense, but it's a static solution. For even greater control, scientists turn to active magnetic shielding. The best analogy here is a pair of noise-canceling headphones. Your headphones have a microphone that listens to the ambient sound around you. Then, the electronics create a sound wave that is the exact opposite of that noise. The two waves cancel each other out, and you hear silence. Active magnetic shielding works the same way. First, a set of highly sensitive magnetic sensors, called fluxgate magnetometers, are placed near the quantum computer. These sensors constantly monitor the ambient magnetic field in real time. This information is fed to a control system, which then sends a precise electrical current through a set of coils wrapped around the experiment. This current generates a magnetic field that is perfectly equal in strength and opposite in direction to the unwanted noise. The two fields cancel each other out, creating a bubble of near-zero magnetic field right where the qubits are. This active approach is incredibly adaptive. It can respond instantly to changes, like a nearby elevator moving or a large piece of equipment being switched on. It also allows for much more compact designs, since you don't need as many thick, heavy layers of passive shielding. The ultimate solution, and what most advanced labs use today, is a hybrid system that combines the best of both worlds. A large, multi-layer passive shield made of mu metal and other alloys does the heavy lifting, cutting down the vast majority of the ambient field. Then, inside this passive shield, an active system of coils and sensors provides the dynamic, fine-tuned cancellation needed to achieve the extreme magnetic stability that high-performance quantum computing demands. But the challenges don't stop there. As quantum chips get bigger and pack more qubits together, the problem of magnetic crosstalk becomes a major issue. To solve this, researchers are now developing on-chip magnetic shielding. This involves building microscopic shielding layers directly into the quantum processor chip itself. These tiny shields can isolate individual qubits from their neighbors, preventing their control signals from interfering with each other. In a completely different approach, some scientists are trying to make the qubits themselves more robust. Researchers at the University of Chicago found that by changing the chemical environment around a qubit, they could make it inherently less sensitive to magnetic noise in the first place. By designing a molecule that naturally shields the qubit at its core, they dramatically increased its coherence time. This idea of chemical shielding is a revolutionary path toward creating tougher qubits that can protect themselves. In the grand quest for a powerful quantum computer, the qubits and the mind-bending algorithms often steal the spotlight. But none of it would be possible without the silent guardian that stands watch over the quantum realm. Magnetic shielding, from giant cocoons of mu metal to intelligent, self-correcting field cancellation systems, is the unsung hero of the quantum age. It is the technology that creates the pristine, quiet space required for quantum bits to exist, to connect, and to compute. Each improvement in shielding technology is another crucial step towards unlocking a new era of computation, one that could help us solve some of humanity's greatest challenges in medicine, materials, and beyond. The shield isn't just a box, it's the enabler of a revolution.